Hello, everyone. Welcome to my talk about high-performance services with gRPC. I want to introduce myself. My name is Matias Zatz, and I've been working here at Cognizant Softvision for around 2 years now as a software engineer and developing solutions for these different projects. I want to encourage you all to drop your questions on the chat box over there so we can address them later. Okay, so I want to start by introducing myself with just what I do here. I'm not just only a software engineer and community lead here at Softvision, but also I am a front-end programming teacher at Horta, Argentina, which is a high school here in Argentina. And that's my email in case you want to drop by any comments, feedback, or questions. It's matias.zatz@softvision.com. I will try to answer you as soon as I can. So without further anticipation, let's dive in this world of gRPC. But first of all, I want to go back to the foundations before talking about gRPC. And that's when I want to talk about RPC. So RPC is basically a remote procedure call. And a remote procedure call is essentially when a computer executes a procedure, which presumably is local on another computer machine over a network. Okay, this means that the procedure you will call it locally in your machine, but it would actually execute in another machine. So as you can see in this little picture, you will have a procedure, in this case P, with these 3 parameters. And just calling it regularly, it will go over the network and will execute in another machine. The cool thing about this is like the implementation of this procedure. It seems like local in your machine, but it's not there. It's actually another machine. That's what's cool about remote procedure calls. As you can read, it doesn't need to exist in the same address space. Okay. So this may seem like some new thing, but actually it's not. It's go back right to the 70s. We're going to talk about that in just a moment. So how an RPC implementation is? Well, basically, the starting off from this client-server architecture, the procedure you will call here in the client, it will go over here to a client stub, what we call it. The stub will pack it. Okay, it's a process called marshalling, which will pack all these parameters you're sending, and it will pass it on to a transport layer, which is this RPC runtime. This RPC runtime will send it over to the server, and here we have the reverse process. It will unpack it and marshal it. It will call the actual procedure on the server machine, and it will return the result all the way back with the same process. It will pack, send, and receive here. That's the most basic RPC implementation. So, as I said, let's just take a moment to talk about history of RPC and distributed computing. So, as you may know, distributed computing, when building distributed computing, the most, let's say, first ideas came down from the late 60s and the early 70s, like RPC, which actually was firstly practically implemented with stubs and everything around the 80s. And then some other concepts like messaging and queuing also were implemented in that time. Mechanisms that maybe seem modern, but they're not. They're from that era. And then moving on for the object-oriented programming, when this object-oriented programming became standard for building large enterprise applications, we have some new players in the game. For example, we have Corba, which is the Common Object Runtime Broker Architecture, which enabled communication between different languages. And also we had COM, VCOM, we have Java, RMMI, if you ever work with Java. And then we had, for instance, SOAP, which is another major player here. SOAP is the XML-based protocol that went over HTTP, and it was widely used among ASP.NET solutions and net solutions. And that led us to the 2000, where web-based APIs come into place. And here we have XML, HTTP, and REST principles were actually introduced in 2002, if I'm not wrong, by Roy Fielding. And that's where we are today. We are with REST solutions, and right now, lately, we have been with modern technologies like GraphQL or gRPC. But I wanted to show you these ones because, just as you see, gRPC is not replacing anything. It fits in this overall spectrum of technologies, and it will have the right use. So now we know something about basic RPC. We can talk about gRPC, which is the mother of this talk. So gRPC, right from the website, it's a high-performance, open-source, universal RPC framework. It was made by Google. And actually, Google implemented RPC services within their infrastructure for a couple of years now. They made like a first implementation, which was called Stubby. And they wanted to scale that implementation and make it open for the public. That's when gRPC comes into place. They couldn't evolve that Stubby, that first implementation, because it was pretty much coupled to Google's infrastructure. So they came out with this, with gRPC. And as you can see, this picture here, this is like the most basic form or gRPC that I can explain to you. We're going to talk about this later, about the proto request and response and everything. But the cool thing about gRPC is that you can connect different services made in different languages, and they can talk to each other without any problems, okay? Because if you can see, these clients have a stub, like we've seen before in RPC, and this stub will communicate with a gRPC server, which can be coded in C++, Python, Java, or anything. And it can talk to these two services without any problems. So a couple of things about gRPC. gRPC is contract-based. It's based on this Protobuf we're going to talk about in just a couple of minutes. It's built on top of HTTP2. That's another major topic we're going to cover today. And thanks to this, it leads me to the next point, which is actually the binary protocol. Okay, so gRPC runs on binary protocol that makes very fast and lightweight. And that's one of the key things about gRPC. And because of this lightweight and fast and effectiveness, it will make effective use of network and effective use of resources. And another major thing about gRPC is that it supports not only one-way communication, but also bidirectional streaming. This is a game changer for everything that's communication between servers or between clients and servers. And we're gonna deep into that later. So what does gRPC mean? It actually means a couple of things. Like the most basic, it's the gRPC remote procedure call. It's a recursive acronym, just like PHP, GNU, Unix, you name it. Some say that the G is for Google, but I don't know. Actually, each iteration of gRPC, each new version of gRPC, the G changes its, sorry. Okay, sorry about that. It changes the G meaning, okay? So as you can see here, each version of gRPC has a new meaning. We're currently on this one. So that's a good thing. You can see everyone here in this link. And so, why should we use gRPC? And the short answer for this, performance. That performance has a couple of reasons behind it. We're gonna talk about first of the protocol buffers and then of HTTP2, which are these two major topics that gRPC covers. So starting with protocol buffers. So protocol buffers are these Google language neutral, platform neutral, and extensible for serializing structured data. And you can think it just like XML, but smaller, faster, and simpler. And we are gonna go with that in just a few minutes. And with the latest Proto 3 language version, the versions are Proto 2 and Proto 3. And Proto 2, it's just no longer used, I think. But with the latest version of this language, protocol buffers support generating code in C#, Java, Python, Objective-C, and a couple of more languages. This makes it pretty simple to implement, okay? Because one of the things that protocol buffer have is that it supports code generation, and we're gonna see it right now. This is an example of Protobuf, how it looks. And just right from the start, you can see this is way much simpler than a JSON and way much more lighter, okay, lightweight. Because JSON is actually more human readable because it's state-based. But protobufs are lighter and they are simpler. So in the end, you will see that sizes between protos and JSONs is relatively big. So some advantages about the protobufs, it's the simple syntax. We're gonna dig in this later, but this is like the basic syntax. It's fast and lightweight, and it has binary serialization. Okay, this is what makes it so fast. Because this message you will have in Protobuf, it will serialize into binary data. And then it will generate code for you. That's one of the major advantages when developing gRPC solutions. And the code generation is made by this Proto-C, which is this executable. It comes with gRPC plugin. And it will generate code from that proto file. Okay, you will define your services and your messages, and you will get your generated code on client and server. And that will make your client and server generated code. One thing worth mentioning about this, the protobufs should be like the same when implemented on the server or on the client. That's why it's contract based. You need to have both protobufs on the 2 points so you can communicate. It's kind of not a disadvantage, but it makes it like difficult to implement in some scenarios. So this is how it looks, a protobuf syntax. We're gonna see this in Visual Studio in a few minutes. But as you can see here, a couple of things worth mentioning. You have some reserved words like the syntax, which it means the version of the protobuf. It's Proto 3 in this case. And every protobuf you will code from now on should be Proto 3. Then you have, for instance, in this case, I'm using it on C#. So I have this option C# namespace that will have this embed namespace. So when I compile this proto, it will generate under this namespace. Then you will define services in which you will have these RPC calls. And you will have also messages you will define. And this will generate your models, okay? So these messages, as you can see here, will generate models. And these models will be inside the methods, it will be created by these services. So as you can see, we don't have data here. We just have the type of the data, the name of the field, and an ordinal number. This is like the position in the message. So this is not like a value or anything. It's just like the ordinal place. So ID will come in the first place, title in second, subtitle in third, and so on. This is pretty important to check because if you change any of these any of these numbers or the position, you may end up with problems. We're going to talk about versioning protobufs because there's a couple of things. So evolving protobufs, it's kind of tricky when you do it because you want to do it right, so you don't introduce any breaking changes. So as I said, existing fields shouldn't be renumbered. Okay, you can just use a number that was probably used by other field. Let's say from this example, we need to remove subtitle. I can just put 1, 2, and 3. The number 3, it will remain reserved. Okay. So this doesn't introduce any breaking change to existing code or existing clients. So another thing, sorry, this reserved, it's when you remove a field or something, you want to reserve that position so nobody uses. Okay. Same goes with field names. You can just put reserved for some names so they can be used. And continuing on with the last thing, existing fields shouldn't have the types changed. Okay. If you're gonna change that, you can do it by using the reserved word one-off, or just upgrade it to a repeated field. Because you have like these modifiers, which are the optional, the required, and the repeated. So new fields shouldn't reuse any previously assigned field, which is the reserved numbers we talk about. And enum defaults, which are indicated when number 0, should be picked such as they make sense looking forward, or set to unspecified. So you have enums in Protobuf. You can define a type of enum, but it should have always a number 0, which will be the default. And another major topic of the performance of gRPC is HTTP2. And opposed to HTTP1, it has some breaking changes, some measure changes, sorry. And first of all, as you can see here, this is like an HTTP package looks like with all these headers and the response. So now this is like split in 2 frames, one from the headers and one from the data. And this data will be, this data frame will be serialized as binary data. That makes it really fast and really lightweight. Also, the headers will be compressed. So HTTP2 supports compression of the headers. So that makes this really, really fast. Some characteristics about HTTP2. It supports request multiplexing over a single TCP connection. We're going to see that now. It supports compression of request headers, as I said, and it uses binary format as the default data serialized. And also HTTP2 supports server push. That's another major change from HTTP1. So the cool thing is that HTTP2 can reuse a single TCP channel and send data, stream data over one single TCP connection, rather than HTTP1. Like you see in this image, maybe for each resource, you need to do one call, one request, and that will open one TCP channel for each request. And instead, on HTTP2, by just having one channel, you can stream all the data. Okay. Actually, I'm gonna demonstrate to you with a cool demo I have here. But as you can see, as I explained, each resource you need to request from the server will open a TCP connection, and it will make one round trip, okay, to the server. But in HTTP2, it will open just one channel and request everything, and it will stream back the things you need. The server push also supports this this kind of caching by the server, because the server can just send resources that things the client will need without the client even just asking so, or not asking yet. So I'm going to show you this cool example by Akamai. So what you're seeing here is this picture of the world, but this picture is composed from little tiles. So as you can see, the overall image is composed by all these images. What I'm going to do now is I'm going to reload this. I'm going to force from the cache, so nothing is cached. And I'm going to go and throttle my connection to a fast 3G, so I can simulate I am on a low bandwidth situation, like you probably are, I don't know, with your phone on the street or something. So we're going to see how HTTP2 works against HTTP1. So I'm going to reload this, and you will see how these tiles will start to reload. So, okay, the request begins, and all these images comes into place. And what you're seeing here on the right is all these TCP channels. When they reach a limit, I think it's like 6 channels, it has to reuse the one available. So here you can see all these requests for each tile of this image. And just see how long it took. And now we're going to see how long it takes HTTP2 to do this. So by using just one channel, it's streaming back all the tiles. And we have almost like 30 seconds of difference. And I'm not even talking about gRPC. It's just by switching from HTTP1 to HTTP2, you see this this performance improvement. And if you can see here, look all these requests HTTP1 made. And if you can see here at the right, I think I cannot zoom it that much. But by using just one channel, it streamed all the data back to the client. That makes it so fast and so secure and reliable and lightweight. So gRPC is built on top of this. So you now maybe probably wondering how fast it is. Well, you can tell here. So going back, we just saw protobufs, how they're made, and we saw what HTTP2, what is all this about. In this part, I want to talk about gRPC versus REST, because one common maybe confusion or wondering that you may be having is if gRPC is going to replace REST, or if it's something you need to use over REST. And we're going to tackle some differences between the two. So first of all, REST relies on text formats like JSON, while gRPC relies on binary data made by the protocol offers. And also REST relies on HTTP1 that we just saw. All the requests we do on REST are over HTTP1, and while gRPC does that on over of HTTP2. And then we have this major thing, major difference between the two, which is the code generation feature. So REST API does not support inbuilt code generation features. You need to use a library like OpenAPI or Swagger to achieve that. But instead, gRPC has this native Protobuf code with Proto-C compiler, which will compile these Protobufs into generated code. One thing worth mentioning, Protobuf wasn't made for gRPC, but gRPC relies heavily on Protobuf. So you can use Protobuf for other implementations if you want. And last, this is another major difference. REST is widely supported by browser, as we all know, as we've been using it. And gRPC requires, for now, like a proxy layer to perform conversions between HTTP 1 and 2. So if we want to use it on the browser, you need to have some proxy in the middle. There's a talk later today by Felipe Ortiz, and he will talk about how to implement gRPC services on a JavaScript environment. So stay tuned for that talk. So is REST over? No, not really. In fact, I think REST will be here for a long, long time. And this is because both REST and gRPC are good fits for different use cases, okay? So gRPC, for instance, is not suitable for a public API. Because of this contract-based structure, it's pretty much strict, okay? So you can implement it anywhere. What is suitable for, actually, is for connecting microservices or connecting, for instance, IoT devices, because it's resource friendly. And it's so lightweight that it can handle those. When you're working with a polyglot environment where you have like too much services written in different languages, with gRPC, they can talk to each other with minimum effort. And from real-time point-to-point communications, that's where we take advantage of the streaming capability of the bidirectional streaming. And also, you can use it, as you saw, low power and low bandwidth networks, okay? Because even if you are running on a low bandwidth environment, by just using HTTP2, you will get awesome results. So I had this like practical example. So let's say you want to interact with purchase services made in .NET. So that's when I say you can just use a public API here with gRPC because it's not suitable for that one. So you will make like a REST call to that services, but that purchase service can talk to the product services over gRPC, and that will make it real fast. So that's why it's a good fit for microservices interaction. Now let's say you have a shipping service, but this shipping service is made in Golang. So you can actually connect it via gRPC with minimum effort, because you see, taking advantage of the stubs, we generate code for Golang natively, and it will have the objects without any serialization. What I'm trying to say is when you're working with JSON, like an intermediate format, you need to serialize and deserialize from JSON to work with. But here in gRPC, by the Proto-C compiler and the Protobufs, you will get native code. Okay, so no more serialization. Each one can talk to each other, and you will have native code. So let's go for some action with gRPC. I want to show you this cool solution we made with Felipe. So let me just get some zoom here. So the basic structure of this project, we have this gRPC server and we have a gRPC client. And we have this REST client we implemented to just check how difficult it was to implement each one of these. So starting off from the server, I have this Protos folder. This is a convention I have. This is a convention that exists. And we have this meeting proto. And as you saw, we start defining the syntax. We define this C# namespace. We're going to see it right now. And we define the services. Okay. So I have a couple of services. Each one of these will represent a procedure that I can call. And you have here the models or the messages that we'll work with. So I will have this get meeting info that will receive a meeting lookup model and will return a meeting model. So we have defined here this message, which is the meeting lookup model, which will have one ID of int 32, and it will come in the first place, and it will return a meeting model, which is this one, which we have ints, strings, bools, you name it. But also we have, for instance, this RPC call, which is get all meetings. We'll take a request and we'll return a stream. Okay, so this is when we talk about different types of RPC. I think the presentation got broken in the middle. Yeah, here it is. So with gRPC, we can define several types of RPCs. We have the unitary RPCs, which are the single RPC, the most common, where you get one model in and you get just one message back. Then we have the server streaming, where I send just a request and will get a couple of responses by the server. Just taking advantage of that TCP connection open, it will start streaming this response. And then we have client streaming. And this is when I send, let's say, a couple of requests to the server. And the server may answer after the first, after the second, that you can handle it, or even after all the message are streamed. And then you have bidirectional streaming. This is like the most complex to implement. And here you have a stream on both sides. So you can send a stream of messages and get a stream of responses, but it can be in any order, right? You can send, I don't know, one message in, one message back, or you can send all the messages in and then get all the message back, and you define that. But that's the bidirectional RPC I was talking about. So coming back here, we have these models here. And as you can see, I have here this repeated meeting model. So as you can see, we can define like this kind of customs by just reusing all the messages. And by repeating, I'm saying I'm gonna send a couple, like I will sell like an array, just for practical purposes, like an array of items with this model. That was repeated means. So whenever you have this proto file, you will see here in properties, you have this property which is compile protobuf. So on each time I rebuild this solution, it will compile this protobuf and will generate my code. And I can set here where do I want this to generate. So in this case, I'm on the server project, so I want to generate stub classes for the server only. But I can actually choose client and server, and it will generate for both client and server generated code. Or I can even say, hey, don't generate. This is mostly used when you define, I don't know, you define a couple of messages in another protobuf, and you can import it, those protobufs here. So you don't need to actually that one to generate. It's just it just won't generate because it's important. And then this will generate some code that we can actually, let me check here. So I have this meeting base. So this is all the generated code by gRPC. So this is where the magic happens. Okay? Each time you rebuild a Protobuf, it will generate all this code. And the cool thing is that you can override those methods to make them what you want to make. So in this case, we have a couple of adds, saves, gets, and all kind of stuff. And we have this namespace I named it before. It's made out of this. And then if you can see here, I have this meeting model, for instance. It gets, so you get this model ready to use. So you mostly don't need to do anything, but just compile that and you will get your generated code. And then, yeah, you can start overriding those methods to make them what you want. But it's pretty easy. When you get the practice, it gets pretty fun to code on gRPC. And then on the client, for instance, I have the same Protobuf. So whenever you are interacting with the server, you need to have the Protobuf itself here. And here, what are we doing is we are calling this method. But as you've seen before, this method, just like RPC, is not on the client, it's on the server. And this will get executed on the server and will get back. But this is all the magic of gRPC. It's implementing local procedures that will be executed on a remote machine via these protobufs. So, and then you have the same implementation, but you made it in REST. So a controller that will do the same. So yeah, it's more human readable and everything, but in the end, when you do the benchmarks, you will see this is much faster. Sorry. So I want to show you some benchmarks runs on this one. Have it run here. So just check the benchmark results when you're comparing REST versus gRPC. So just by getting a large payload as a list, you see here on gRPC the times. It doesn't get not even close to 500. And if you had the same call on REST, you could see, depending on the environment, you will have more or less, but it's like a huge difference. It's kind of 7 to 10 times more faster gRPC than REST in most cases. And this is all because not only the HTTP2, but also the protobufs, because they are lighter than the JSON's payload. So we get pretty awesome results if you implement correctly the gRPC services. So I encourage you to dive in this world. It's pretty fun and pretty amazing what you can achieve. And they have a lot of documentation, so you can just go to the website and check it on, download a sample code, and you can get started. So any questions we have?
We don't have any questions so far.
Okay, we can give a couple of minutes. Well, if there's no questions, I want to thank you for joining to this talk. I really hope you learned something today. And I want to thank you. I want to thank some teammates, Felipe, Romaldo, Luis, and Pedro, who had been very supportive and helped me with this talk. So kudos to them, and check on their talks they will have later. Both Felipe will talk about the gRPC implemented in JavaScript, and Romaldo will have a talk with Emiliano about leading in tech and culture. So, okay, if no questions arise, I think we can call this a wrap, and hope I see you next year, and just enjoy the rest of Promos Week. Thank you.